I got up a bit late today, so I'm filming just as the sun's about to set. So I have a lighting problem, just too much light streaming onto the board. Maybe you can't see certain parts. Okay, now a few more details about the mechanics, the nature of the TM, the Turing machine. So initially on the tape, when you start your computing process, you'll have an input stream, just the same way you would with a finite automaton, okay? And the rest of the tape, this infinite tape, is just full of blanks, okay? There's no symbol, well, unless you call a blank a symbol. So the whole tape is full of blanks except for a contiguous input stream. So there are no blanks inside the stream. Okay, so it's contiguous. So all its symbols will be symbols different from the blank. Now, the blank is usually represented as a symbol that looks like, well, I'll just draw it. It's like that. Looks like a dish with sort of turned up ends like that. So now I've never come across a label for that particular symbol. Well, other than say the blank symbol, but it sort of looks a bit like a cup, right? Like that, or a tray or something. Anyway, so that symbol is used to represent the blank square. Okay, so when the Turing machine starts, at the beginning, the infinite tape will be all blanks, except for a contiguous input string, which consists of other symbols, other than blank. Okay. What else can I say about it? So it uses the tape to store information. You can read and write on the tape, as I was saying a bit before. Now, to be able to read information that's written earlier, it can move. Remember, the read-write head can move along the tape, or equivalently, the read-write head stays where it is, stays fixed, and the tape gets moved. But I think it's probably conceptually easier to imagine the read-write head moving across the tape. Okay, so it can read information that it previously wrote, and that's memory. Right? That's how the TM has memory, and it has infinite memory because the tape is infinitely long. Okay, now it may be very inefficient because it's got to move from square to square to square, but in principle, its memory is infinite. It can store anything effectively, right? A few other comments. The Turing machine just keeps computing. It doesn't stop. In other words, it does not halt. That's the technical word used in this context of Turing machines. Halt, H-A-L-T. Hence the halting problem rather than the stopping problem. But same thing. All right. So it just keeps computing away until it gets in a state that's either accept or reject, and they're two separate states. And there's only one accept state and there's only one reject state. Okay, so Sipser doesn't mention it explicitly, but the Turing machine, the TM, is a deterministic machine, right? There's only one next state. Okay, that's the definition of determinism. Whereas a non-deterministic machine, you can have more than one next state. So the Turing machine is determinist until, well, the model we're giving you now is determinist. Okay, what else can we say? So there's only one accept state and one reject state, and until the machine gets in one of those two states, it will just keep going, right? Infinitely if needed, right? And it'll just go on forever until it lands in either an accept state or a reject state. And there's only one of each, and these two are different. Okay. All right. So here's your control. We've seen diagrams like this before. So the control, what does that contain? What information does the control have? Well, it has the current state of the machine, just like a finite automaton, and it has all the transition rules. So it knows what to do. Now, this arrow here represents the position of the read-write head. Okay, and so the read-write head is now looking at the square on the tape. Here's the tape. Now this tape is infinite this way, but finite that way. Right? That would be the end of the tape. That's so a particular variation type of TM. Okay. So the read-write head is currently positioned on this square, which contains the symbol little a. Okay, so this A and here's a B, these various squares on the tape. These would be symbols of your input alphabet, tape alphabet. They're two different things in the TM. I'm jumping ahead a little, but gets a bit subtle. How many alphabets are you going to have for the TM? And the formal definition, which we'll get onto later, there are two different alphabets. Similar to the stack machine, the PDA. It had an alphabet for the input stream, and it had another alphabet for the stack. So the input alphabet, the input stream alphabet, and the stack alphabet. For a TM, something similar, you'll have details. It's session 3 or 4. We'll get onto that. Okay, so that's a sort of representation of the sun has now gone behind the building, so now there's less light. So I'll open the curtains a bit. Just a minute. So, might be interesting now to talk about, we've been talking about the similarities between a TM and the previous two automata. How about the differences? Well, there's a list here given. So, now a TM can read and write. It can do both on its tape, on its memory. Okay, with the stack, well, you could do that. Actually, when I think about it, the stack you could write onto the stack. That's called pushing, and you could read it, and that was popping. That's what the text says. I query that. Okay. Anyway, so it just says a TM can both write on the tape and read from it. Okay. Well, it has a tape rather than a stack. Second thing is the read-write head. It can move both left and right. Okay, one square either side of the current position. The tape's infinite. It just goes on forever, either both ways or just in one direction. And this now here's some real information that's sort of new, maybe a little surprising. When the TM, when it goes into the state reject or the state accept, as soon as it does that, it stops working. That's it. It halts. Okay. It doesn't continue doing other things the way the previous automata were doing. The non-deterministic PDA, for example, could go into an accept state and then continue processing. Whereas a Turing machine, the moment it goes into either the accept state, and there's only one of them, or the reject state, and there's only one of them, it stops functioning. That's it. It's done its job. Okay. It's either accepted or rejected, and that's it. It stops. That's this one. Right. Well, what we're going to do now, before, in fact, it will be 2 further sessions. It'll be session 4 on the board before we get into the formal definition of a Turing machine, which is actually a 7 tuple. There are 7 things in the list of the formal description of that machine. So before we do that, for didactic purposes, the essential difference between the Anglo-Saxons and the French strongly have a tradition of giving definitions first. They want generalizations before particulars, and the Anglo-Saxons are sharply critical of that tradition because it's very poor teaching. So the didactics of the French approach, I've mentioned this before, and it's a sort of hobby horse of mine. The didactics of the French traditional way, I think, is inferior. So if you're being taught in the French tradition and your professor teaching you this kind of stuff, or pure math, without and you're learning something, and it's often useful, didactically useful, to be given an example so that you get a feel for what it is that all these formal definitions are talking about. Right? If you're given a formal definition with lots of concepts that you're unfamiliar with, then that definition will be just meaningless to you until you have some familiarity with what the definitions are talking about. Okay? So, I've lived in both traditions, and I know which one I prefer when it comes to learning something. Later, once you've learned the concept, and then you want rigor, well, then the French are great. They're great at rigor, but their didactic quality is inferior, I'd say, to the Anglo-Saxons, the Americans, and the British. So hopefully get the best of both worlds. So get the strong didactic traditions of the Anglo-Saxons and combine that with the strong rigor